For over 2,000 years, how we understood matter was based on this really simple, kind of comforting idea.
Right, that the atom was just this hard, indivisible particle. Couldn't be broken, couldn't be changed.
Exactly. That was sort of the law of the universe, from the ancient Greeks right up to 19th century chemists.
And that basic belief that the atom was, well, the final thing, the ultimate building block you couldn't crack, it held firm.
Until
Ernest Rutherford came along, the guy who actually confirmed atoms existed, but at the same time proved they weren't indestructible. Not at all. Mutable, complex, definitely destructible.
So today, we're doing a deep dive into Rutherford's absolutely revolutionary career. He's known as the father of nuclear physics, right?
Universally, yes. And it's quite a story.
It really is. We're looking at his whole journey, starting as a flax farmer's son way out in New Zealand, and ending up, well, a British baron, heading the world's top physics lab.
Yeah, the sources really paint the picture. He was known for, bold inferences from apt experiments, disciplined common sense, and inspired neglect of what other people thought important.
I love that last part. He just didn't care about following the crowd.
Not if his experiments told him otherwise.
So our mission here is to unpack how his discoveries unfolded. These kind of surprising steps from figuring out weird rays to actually mapping the inside of the atom, the nucleus. It totally changed how we see matter.
It really did. So where should we start? Cambridge.
Let's start there. He arrives at the Cavendish Laboratory in Cambridge, 1895. He's young, just 24, an advanced research student.
And he lands in a pretty good spot. J.J. Thomson is there, the head honcho. Rutherford liked him, said he was not fossilized at all. High praise.
Yeah. And Rutherford hits the ground running. At first, he's working on radio waves, which was the really hot topic then.
Right, and he does pretty well. Sets a record, doesn't he? Longest transmission distance at the time.
Yeah, half a mile on Leap Day, 1896. But his focus shifts pretty quickly. Things were happening fast in physics back then.
Oh, incredibly fast.
Yeah.
You had Röntgen discovering X-rays in 95, then Becquerel finding these uranium rays in 96, just boom, boom, boom.
So Rutherford and Thomson dive into studying how these rays affect gases, specifically how they ionize them.
Which basically means the rays knock electrons off the gas molecules, splitting them into positive and negative ions. It was sort of the first clue that maybe you could break matter down somehow.
And this leads Rutherford to his first really big observation about those uranium rays. He figures out they're not all the same.
Correct. He found two distinct types. The first he called alpha.
Alpha. Okay, what were its properties?
Highly ionizing, meaning it created a lot of charge as it passed through gas. But, and this is key, very low penetration. You could stop it with just like a few thin sheets of aluminum foil.
Okay, so like a bowling ball makes a big impact but doesn't go far.
Good analogy. And then there was the second type, beta.
Beta rays. Different how?
Almost the opposite. Lightly ionizing, didn't create much charge, but had way, way higher penetration. They zipped right through things, more like tiny needles.
Alpha and beta. That simple categorization seems, well, foundational now.
Absolutely. It underpinned everything he did later. But the really huge conceptual leap, the thing that basically started nuclear physics, that happened after he left Cambridge.
Right. He moves. Where did he go?
McGill University. In Montreal, Canada, 1898. They gave him a brand new lab, loads of funding. He was ambitious, famously said he wanted to knock the shine out of the Yankees.
He definitely had a way with words. And did he?
He certainly made a huge impact, started working with thorium, another radioactive element, and that led to something really weird.
Weird how?
He found this emanation, that's what he called it. It was like a radioactive gas, or maybe a particle that seemed to come off the thorium but decayed incredibly quickly.
A gas, so not just rays, but actual matter coming off.
Exactly. It was perplexing. It was ghostly. It vanished almost instantly if it drifted away, but it was definitely substantial, definitely material, left radioactivity behind on surfaces.
Wow. Okay, that must have been confusing.
Totally. But it led him, along with a chemist named Frederick Soddy, to their big theory in 1902, the Rutherford-Soddy theory.
And what was the core idea?
This was the bombshell. They realized that when an atom emitted an alpha or a beta particle, that was the radioactive change. The very act of decaying meant the atom was transforming.
Transforming into a different element.
Precisely. One chemical element was literally turning into another, all by itself. spontaneous transmutation.
Huge. That blows up the whole indestructible atom idea completely.
Completely. They even showed it experimentally, plotted these amazing curves. You could see the decay of what they called thorium X, the daughter product, and at the same time, the parent thorium recovering its radioactivity. They perfectly complemented each other.
And didn't Rutherford put those curves somewhere special later?
He did. When he was made a baron years later, he put those exact crossing decay curves right onto his baronial shield. Shows you how fundamental he thought it was.
It's like branding for physics, but the implication.
Oh, it was immense. Soddy apparently yelled, "Rutherford, this is transmutation!" And Rutherford snapped back, "For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists."
Huh. But they were right. The alchemist had the basic idea, just not the mechanism.
Exactly. Nature was doing it all along. They just didn't know it.
Okay, so atoms can change. They're not fixed. Now, Rutherford needed to figure out what those alpha particles actually were, which takes us to Manchester, right?
Right.
His next big phase.
Right. He moves to the University of Manchester in 1907, and he spends years trying to pin down the alpha particle's identity, measuring its charge-to-mass ratio, E/m.
That sounds difficult. These things are tiny and fast.
Incredibly difficult, grueling work. His hunch was that it was basically a helium atom that had lost 2 electrons, so doubly ionized helium, mass 4 times hydrogen, charge +2.
And how did he prove that? He needed strong fields, right?
Yeah.
To bend their path.
Very strong, electric fields especially. And that leads to that great story. He was using this powerful radium source Marie Curie had given him.
Oh yeah, this shocking one.
That's the one. He finally gets the alphas to bend, gets super excited, leans over, and accidentally grounds the whole high-voltage apparatus right through himself.
Ouch.
Said he danced like a dervish. Lab safety wasn't quite what it is today.
Definitely not. But he got the measurement.
He did. And by 1908, he and Hans Geiger, that Geiger developed a method to actually count individual alpha particles using an early version of the Geiger counter.
Counting single atoms, essentially. Amazing.
And then the clincher. They trapped alpha particles in a tube completely free of helium, waited, then they ran an electric discharge through the tube,
Okay.
and they saw the unmistakable spectrum lines of helium gas. Proof positive. The alpha particle was a helium nucleus.
Okay, so the alpha particle is identified. Heavy, fast, positive charge. Helium nucleus. That knowledge must have been crucial for what came next.
Absolutely critical. It set the stage for maybe the most famous experiment in physics history, the gold foil experiment. The incredible event, as Rutherford called it, 1909.
Right. He gets Geiger and a student, Ernest Marsden, to fire these alpha particles at a really, really thin sheet of gold foil.
Yeah, incredibly thin, like 4/10,000ths of a millimeter, basically just a few hundred atoms thick.
And the thinking at the time, based on J.J. Thomson's model, what did they expect?
Well, Thomson's model was the plum pudding. You had the sort of diffuse, spread out cloud of positive charge making up the atom's bulk, with tiny negative electrons, the plums, scattered inside.
Okay, so if that's the atom.
Then these big, fast alpha particles should just punch right through, like shooting a cannonball through mist, maybe a tiny deflection here and there, but basically straight through.
But that's not what happened.
Not entirely. Most went straight through, yes, but very small fraction, about 1 in 8,000. Bounce back.
Bounce back towards the source.
Right back. Yeah. Sometimes deflected at huge angles. Rutherford was absolutely stunned.
That's the tissue paper quote, isn't it?
That's the one. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you."
You can just feel the shock in that statement. What did he conclude?
It took him a while to work it out. Apparently he mulled it over for months. But his inference was revolutionary. The atomic nucleus.
The nucleus, meaning?
Meaning, to make something as heavy and fast as an alpha particle bounce back like that, almost all the atom's mass and all of its positive charge had to be concentrated in an incredibly tiny, dense central core. The nucleus.
And the rest of the atom.
Mostly empty space. With the electrons orbiting that nucleus somehow.
The planetary model we all learn in school. But, hang on, didn't that immediately create a problem? With classical physics?
A massive problem. According to the physics of the day, those orbiting electrons should be constantly radiating energy away.
Because they're accelerating, changing direction.
Exactly. And if they radiate energy, they lose speed and they should spiral instantly into the nucleus. Bang, atom collapses.
So his model explained the scattering, but predicted atoms shouldn't exist.
Pretty much. An incredible leap forward, immediately followed by this giant theoretical headache. The nuclear atom had to be real, the experiment proved it, but it was fundamentally unstable by the known laws.
Talk about a cliffhanger. How did they solve that?
Physics was moving incredibly fast then. Niels Bohr, a young Danish physicist, arrived in Manchester in 1912. He took Rutherford's nuclear model.
And applied quantum theory. Max Planck's new ideas.
Precisely. Bohr basically said, okay, classical rules don't apply inside the atom. He proposed that electrons could only exist in specific fixed orbits or stationary states without radiating energy. They could jump between orbits emitting or absorbing light, but they couldn't spiral in.
That fixed the stability problem.
It did. It was the birth of the quantum theory of the atom, a huge synthesis of Rutherford's experimental discovery and Planck's quantum idea.
And around the same time, someone else in Rutherford's circle made another key discovery.
Moseley.
Henry Moseley, yes. Working between 1913 and 1914, he used X-ray spectra. He was looking at the X-rays emitted by different elements.
And he found a pattern.
A crucial pattern. He found that an element's fundamental identity, its place in the periodic table, wasn't really determined by its atomic weight, how heavy it was.
But by its
Atomic number, which he showed corresponded to the amount of positive charge in the nucleus. The number of protons, essentially, though the proton itself wasn't fully understood yet. Z, the atomic number, that's the element's true ID tag.
Wow. So it's the nuclear charge, not the total mass.
Exactly. And that cleared up a huge mess in the periodic table, especially with all the radioactive elements they were discovering. Sometimes they had elements that behaved identically chemically, but had slightly different weights.
Isotopes. Moseley's work provided the fundamental basis for understanding them. It all locked into place. The nucleus, the atomic number, the isotopes. An incredible few years, 1909 to 1913, just transformed physics and chemistry.
Absolute stunning pace. Okay, let's move to the final phase of his career. But first, World War I intervenes. That must have disrupted things.
Hugely. Science didn't stop, but its focus shifted dramatically. Rutherford threw himself into the war effort, became a leader in mobilizing British science.
What kind of work did he do?
A lot of it focused on detecting German U-boats. That was a massive threat. He worked on underwater acoustics, studying how sound travels through water.
Hydrophones, leading to sonar.
Exactly. His group's work on these acoustical detection devices laid the foundation for modern sonar technology. Practical application driven by wartime need.
But the war had a cost for science too, didn't it? A tragic one.
It did. Henry Moseley, the brilliant young physicist who just figured out the atomic number, he volunteered for service and was killed in action at Gallipoli in 1915. Oh, what a loss. Just imagine what else he might have discovered.
A terrible loss of potential, yes.
After the war, Rutherford moves again, right? Back to Cambridge.
Yes, in 1919, he takes over from J.J. Thomson as the head of the Cavendish Laboratory.
Yeah.
And gets right back to his main passion, smashing atoms.
But this time, not just observing natural decay, but causing it.
Exactly. Artificial disintegration. He starts bombarding nitrogen gas with his favorite tool, alpha particles.
And what happens?
He finds that sometimes an alpha particle hits a nitrogen nucleus and knocks something out. And that something turns out to be a proton, a hydrogen nucleus.
So he'd literally knocked a piece off the nitrogen nucleus and turned nitrogen into oxygen, I think?
Oxygen, yes. He had achieved artificial transmutation, done in the lab what nature did spontaneously, and it confirmed the proton was a fundamental part of the nucleus.
So the nucleus contains protons, but there was still something missing, wasn't there? The weight didn't always add up. Right. The atomic number, protons, determined the element, but the atomic weight was often much higher. Rutherford himself suspected there had to be another particle in there, something with mass, but no charge.
A neutral particle?
He speculated about it as early as 1920, called it a neutron, and then, building directly on Rutherford's ideas and experiments, his second-in-command at the Cavendish, James Chadwick.
He finds it.
He confirms the existence of the neutron in 1932, a particle with roughly the mass of a proton, but electrically neutral.
And that discovery was huge for nuclear physics, right?
Yeah.
Why was the neutron so important?
Because it was the perfect projectile. Think about it. If you want to probe or break a nucleus, which is positively charged, firing another positive particle like a proton or an alpha particle at it is hard. Like charges repel.
Right, the positive nucleus pushes it away.
Exactly, but the neutron, no charge. It could just sail right past the electrical repulsion and smack right into the nucleus. It was the ideal bullet for causing nuclear reactions.
Okay, so the toolkit is complete. Protons, neutrons, electrons, the structure is clear. What's next? Actually splitting the atom with man-made machines.
That came incredibly quickly after the neutron discovery. Same year, in fact, 1932 again. There was theoretical work by George Gamow using quantum mechanics.
The tunnel effect.
Right. Gamow showed that thanks to quantum tunneling, you didn't necessarily need particles with enormous energy to penetrate the nucleus. Lower energies might work.
Which meant maybe you didn't need radioactive sources. You could use machines.
Precisely. It inspired two other researchers in Rutherford's lab, John Cockcroft and Ernest Walton. They built a particle accelerator, relatively modest by today's standards, but capable of about 710,000 electron volts.
And they used it to fire protons.
Photons, yes,
Wow.
at a lithium target.
And it worked.
It worked. In 1932, they successfully split the lithium nucleus, hit it with a proton, and it broke apart into two alpha particles, flying off with considerable energy.
Man-made atomic fission.
Yeah.
And Rutherford was there.
He was. Apparently, he came into the darkened room where they were seeing the scintillations, the tiny flashes made by the alpha particles hitting a screen, and he confirmed the results himself.
What do you say?
Famously, he declared, "I should know an alpha particle when I see one, for I was in at the birth of the alpha particle and have been observing them ever since." A wonderful full circle moment for him.
Absolutely. Master of the alpha particle right from the start. But here's the big irony, isn't it? Even after seeing atoms split, releasing energy, Rutherford was skeptical about nuclear power.
Deeply skeptical about getting useful energy out of it. In 1933, just a year after Cockcroft and Walton's success, he gave a speech.
And he basically said it was moonshine.
Pretty much. His reasoning was based on efficiency. Cockcroft and Walton's experiment was amazing, but only about 1 proton in a million actually caused a lithium nucleus to split. The energy input was far greater than the output.
So no chain reaction.
He argued that a self-sustaining chain reaction where one split triggers others obviously does not happen. He even added that if it did, we should long ago have had a gigantic explosion in our laboratories.
Wow. He predicted the outcome, a gigantic explosion, while dismissing its possibility. Just a few years before fission and chain reactions were truly understood.
Incredible historical irony, isn't it? He saw the potential energy, but couldn't quite see how to unlock it efficiently.
Sadly, he didn't live to see those later developments. He died relatively young, didn't he?
Quite suddenly, yes. In 1937, it wasn't some lab accident, but complications from a strangulated hernia. A rather mundane end for such a revolutionary figure.
But he received the highest honors.
Yeah.
Buried in Westminster Abbey.
Yes, right near Sir Isaac Newton. A fitting final resting place. Baron Rutherford of Nelson, the ultimate recognition.
His career really is this incredible bridge from almost alchemy, the idea of transmutation, right through to the foundations of nuclear physics.
He defined the atom, showed how it naturally changed, and then showed how we could change it ourselves. Just immense contributions.
And fittingly, he's remembered today with an element named after him, Rutherfordium.
Element 104. But here's a final twist for you.
Oh.
Unlike the stable elements he first studied, or even the naturally decaying ones like uranium, Rutherfordium is entirely man-made and incredibly unstable.
How unstable?
Its most stable isotope has a half-life of only about 70 seconds.
70 seconds.
Yeah. As our sources note, it's so ephemeral, this element named after him, this ultimate product of the alchemist's art. He proved possible that right now there may not be a single atom of it in the entire universe. It only exists when we deliberately make it in accelerators.
That's quite a thought. From discovering the building blocks of nature to creating things that barely exist.
It really captures the shift he oversaw.
So maybe something for you, the listener, to think about. Consider that incredible change in scale during Rutherford's time. He started with tabletop gear, gold foil, simple screens, early counters.
Just like microscopes, really.
Right. And by the end of his life, and certainly soon after, you have these huge machines. Cockcroft and Walton's accelerator was just the start. Then cyclotrons, eventually reactors.
The whole nature of physics experimentation changed. From observing what nature does on its own to actively forcing matter into new, often unstable forms that don't exist naturally here on Earth. That shift from observer to creator, maybe that's the deepest legacy of the path Rutherford set us on.